Have you ever observed the rainbow on a rainy day and paused for a second? This beautiful phenomenon, where raindrops act as millions of small prisms, makes an important characteristic of sunlight visible. Sunlight consists of electromagnetic waves with many different wavelengths, some of which in the rainbow we can see as colors. I'll start, give you some basics about spectral imaging before I explain some benefits of seeing spectral. I'll then show you how the data acquisition works and make a short application example before I show some other applications. I'll end with some desired camera characteristics. So the electromagnetic spectrum, we can only see a very small part of it with our human eyes, roughly between 400 and 750 nanometers. On the lower end of the spectrum, it extends into the ultraviolet. On the other end, above the red, it extends into the infrared region of the spectrum. We will hear a bit more about the infrared later on. So if we had only one receptor in the visible range, we would see the world in different shades of gray. We would see no colors because we would not be able to differentiate the different wavelengths. This would be a pretty boring world. And luckily, most of us can see the world in color. This is because the human visual system has three so-called cones. So a short cone, a medium cone, and a long cone. And only because of these three different receptors, we can see beautiful colors like this. So for example, if we have a blue light source at around 450 nanometers, we get a strong signal on the short receptor and very small signals on the medium and long receptors. Our brain brings this together so we can see a blue color. Color imaging sensors work pretty much in the same way with the well-known Bayer pattern. So if we have a monochrome sensor, we only have a certain sensitivity in a certain range, but we cannot distinguish any wavelengths. So we have no spectral information. On an RGB sensor, where we have overlapping band passes, we have only very limited potential for spectral information. We can differentiate some colors, but not much more information. In multispectral imaging, we typically have between 2 and 10 different filters with different different widths. So it can be very narrow filters, it can be wide filters, all depending on the application. In hyperspectral imaging, we usually have many more than 10, usually more than even 100 different filters. And we also usually observe quite a continuous spectrum. We observe a continuous spectrum. As a comparison, I also put here spectroscopy, which observes just one point, but with pretty much continuous spectral information. So what are now the benefits of spectral imaging? If we have a monochrome image, it is hard for us to distinguish many different things. So on this image, we can maybe distinguish 4, maybe 5 different shades of gray. If I apply a red filter, which is just the red channel, I can see that I have a lot of red information in the middle and also to the sides. If I now also add a green filter, I see, okay, so I have a lot of green here, a lot of green here. In the end, the blue filter, I have a lot of blue in the big pot and back here. And if I bring all of this together, I see many different colors. So this is a basic property of spectral imaging, that it gives me more information than if I don't have any differentiation. So generally I can say the more spectral data I have, the more information I can extract from the image. I can start to differentiate different materials. I can even identify some material characteristics. For example, I can determine the water content of certain materials, or even the material composition. So how can I acquire such an image? There's commonly different techniques used. I'll start with the whisk broom technique, which is kind of a not much used anymore technique. There I observe pixel by pixel a region, much like I do use a whisk broom. So I scan the whole image pixel by pixel and refract the spectral information onto a line sensor. Much more commonly used is the push broom method, which observes one line at a time. And I either scan the sample line by line, or the sample runs itself over this line. And the line is then refracted onto an area sensor, and in this way I build up a so-called hyperspectral data cube. Yet another method is the staring method, where I take picture by picture, each with a different filter. So I build the image stack filter by filter, image by image. Lastly, there's also the snapshot method, where in just one shot I get the spatial information and the spectral information. This usually requires quite a sophisticated arrangement of mirrors and lenses. So after this rather theoretic approach, let's now have an application example. On the image above, I have 3 different powders. Yet from just looking at it, it is not possible to distinguish any. So for each of the materials, we had the spectral data recorded. So we see the spectrum from the lower end of the visible range, roughly 350, up onto the shortwave infrared region. We have here sodium carbonate, which is also used as, or known as, washing soda, and is used in many washing detergents as water softener or stain remover. We can see here that the spectral information is pretty much flat over a wide range of the spectrum. If we now look at the second powder on the image, on the lower part, it is natron. Is used often in pastries to make them fluffy. If we now observe the spectral curve, we see in the beginning in the visible range, the curve is like the one before, quite flat. But then in the infrared region, or the shortwave infrared region, above around 1,000 nanometers, it drops suddenly. The third powder on the upper left is powdered sugar. This is often sprinkled onto cakes, I'm sure you know. In the visible range again, it is quite flat, the spectral curve, but after around 1,000, it starts to get very interesting. This is an interesting characteristic in many materials, that we don't see a very interesting spectral curve in the visible range. But if we look at the infrared spectral range, curves become very interesting, and we start to be able to separate materials, which, if we look at only the visible spectrum, would not be possible. So if we look at those powders now with a regular monochrome sensor, as expected, we cannot distinguish them. All curves are pretty much flat in that region. That means the sensor is quite saturated, and yeah, no distinction possible. If we now take a color imager and try to differentiate the powders with the 3 RGB filters, we still see no distinction possible. So let's now consider the infrared region. Maybe we have more luck in that we can distinguish them. So if we take a shortwave infrared camera, a SWIR camera, I had hoped well that we might be able to distinguish it, but still no distinction possible. The reason for this is that at the lower part of the SWIR region, the curve is still very high and is able for all the 3 substances to saturate the sensor quite well. So what do we do now? Okay, no distinction possible. So now I have an idea. I take a bandpass at 1650 nanometer, a very narrow bandpass with only a width of 35 nanometers, and suddenly the picture changes. Suddenly I'm able to differentiate the 3 powders quite clearly. So if we look at the curves in that region, we see that the sodium carbonate on the upper right side still has a strong signal and is therefore quite saturated. The powdered sugar, which is somewhere in between the other 2 curves, we see as gray. And the natron, which drops a lot, we can see black here. So what I want to show with this example is you don't always need to observe the whole spectrum. Sometimes it can be enough if you know exactly what you want to do, if you know the substances you want to differentiate. Sometimes it is possible to use only one sensor. Sorry, one filter. So depending on the task at hand, it really depends. One filter can be quite enough. Can be a very small and robust solution, as the filter can be integrated into the camera. And if we say it a bit salope, it could be a hyperspectral solution reduced to one relevant bandpass. Of course, this is not always possible. So on this example here, we see the spectral curves of different plastics: polyester, PVC, PP, polyethylene, and PS. And here it would not be possible to just use one filter to differentiate those. The curves are just too similar. However, here we could use, for example, 7 filters, and we are able to distinguish quite many of the plastics. So as I said, it's always very application specific how many filters you need. If one filter is enough, if you need a multispectral solution, or if you have to go for a hyperspectral solution. So let's now see some other applications for hyperspectral imaging. It is often used in food sorting. I can detect different degrees of ripeness in certain fruits, or I can detect impurities in my materials, or also foul spots. I already mentioned recycling, so I can separate different plastics. Also, it is used in waste separation, so if I have, in waste separation, I never know what kind of materials I have. Can have so many. And is also used in separation of building materials. It can also be used in precision agriculture. This is often in airborne systems. And we can, for example, detect the moisture content of different plants. Sometimes it's even possible to detect the nutrient level of the crops that I observe. Other applications in aerial sensing are mineralogy, to detect different rock formations and classify them. More on the military side is reconnaissance, where I also fly over large areas. And actually where hyperspectral imaging started was in space exploration, because we can detect different materials from faraway planets. So in the end, I would like to also ask about some desired camera characteristic for a hyperspectral solution. Nowadays, we often push-broom method is used, as I described, where I run over a line and let it run as quickly as possible. So high frame rates are very important there. Another important factor is a high spectral sensitivity. On the right side, you can see a spectral curve of our Gold Eye cameras. And we see that it has a very high sensitivity over the whole spectral range. Another important characteristic to be able to distinguish even the smallest signals is that we have low noise in the camera and also high linearity. For infrared cameras, like the SWIR cameras, it is also very important to have stabilized operation conditions. Only in that way I can make sure that I get reliable results, which otherwise, if the temperature of the sensor fluctuates a lot, I can get a lot of different measurements. So I hope that I could start your interest a little bit about hyperspectral imaging. If you want to talk about a little bit in more detail, or also see this application that I presented in more detail, I welcome you to visit our booth, F62, where we show this as a real working example. And I thank you for your attention. Thank you.